Section 8.3, if you remember before our test at the end of the last unit, the very last thing at section 8.2 is we filled in a little table with the different types of quadrilaterals, the different types of four-sided figures. And I had told you at the time that wasn't going to be on the test, but it was just part of the section. We would be linking up with quadrilaterals again. Well, here we are. We're going to be talking in section 8.3 about the perimeter and the area of our polygons. Most of our focus is going to be on things that have either 3 or 4 sides, just because they have kind of the most straightforward ways to figure out the perimeter and area. So first off, the idea of perimeter. Now, I am not for memorizing formulas when I do not have to memorize a formula. Okay, so for perimeter, I'm not going to give you any formula. You probably had a teacher at some point that gave you a formula for the perimeter of a rectangle or something. There is no need for it, because the perimeter of any figure, is simply the sum of the lengths of the sides of that figure. And in case you don't know what the word sum means, S-U-M, the word, well, you tell me, what does the word sum, S-U-M, mean? I'm sorry, what'd you say? Add it up. Perfect. The total. So all you do when I ask you, and I'm going to ask you on the next test, what you see here is exactly how the next test is going to look like. Okay, when I say what's the perimeter of this figure, you're just going to look at the figure and you're going to add up the sides. So I've got my first example. This is the trapezoid. The reason I've given this example is I just want to make sure we're adding up the right things. Perimeter just means the distance around the outside. Okay, so what are the measurements that I'm going to need to add together in order to figure out the perimeter here? All right, great. I'm just going to go clockwise all the way around. So 16, you're right, plus 13. I'm going to use my units, then 6. And then plus 13. It does not matter what order you add these things in. I went in a little bit of a different order than was told to me. I wasn't trying to be contrary or anything like that. Why is the 12 not included, you might be asking? Well, that is something that we'll use in a different problem later. That is telling us the distance between the top and the bottom of this. It is not an edge. Okay, you'll also notice in the figure that is dotted, okay, to clue you in that is not an edge of the figure. We are only adding up the edges. Now, perimeter is a linear measurement. If this was a piece of property, then we would be walking around the outside. So our units are going to be a linear, a one-dimensional unit. So here's my calculator. You got yours, 16 plus 13 plus 13 plus 6 turns out to be 48. And then the units on perimeter are just linear, so 48 inches. There we go, done. I've got a problem or two for you, but before you do it, any question, comment, or concern about finding the perimeter of something? All right, then just do the next example, or exercise 1. The reason I've given this example is not all the sides are labeled, but you need to remember to add up all the sides when you find the perimeter. So give it a try. So when I do the perimeter of this, what do I have to add together to do it? Great, thank you. So I'm just going to label my drawing just in case you didn't. When we're finding the perimeter, we have to remember all the dimensions, even if not labeled. This is a rectangle that we mentioned again at the end of section 8.2. And in a rectangle, opposing sides are equal. So this side up here is 8 feet and this side over here is 4 feet. So whatever order you added these in, you just can't forget to add them all. So again, the order doesn't matter. I'm just going to start at the top and go clockwise. 8 feet plus 4 feet plus 8 feet plus 4 feet. Okay, so as long as you have those 4 measurements, whatever order, you're not wrong if you added them in a different order. Whatever you did, we should all get 24. And what are the units of my perimeter? Feet, yes. Are we still doing okay? All right, then please do exercise 2. It's another trapezoid, just to let you run through the key bits. Okay, so once again, my perimeter, just going to add up the sides. I'm going to start at the top again. That's just my habit. It's not what you have to do. The 5 inches plus the 25 inches plus the 19 inches plus the 25 inches. And what do we get when we pop all that into the calculator? 74, and then the units, thank you for saying those as well, inches. Units are important in this. When you are given units, please give units as part of your answer. Okay, that's a detail that's important. Okay, so that's all I have to say about perimeter. Any figure, however many sides, I might give you a 5-sided figure. It doesn't matter how many sides. Whatever you're given, you just add up the sides to find the perimeter. Are we okay with that? Okay, so the next thing we're going to talk about then is the measure of the inside of a polygon, the region part of it, the 2-dimensional part. And the word that we give to that inside the polygon is called the area. And it is the measure of the region inside the boundaries of a polygon. So for instance, if you've ever put carpet in your house, or if you've put tile down, then that is area. Okay, that's 2-dimensional. There's a length and a width. So we talked about degrees of freedom real quick. When I'm inside a polygon, I can either go forward or backward. That's one way, or left or right. That's the second way. Okay, area is a 2-dimensional. So my goal here, what I want for you is, as we're going through the different regions you're responsible for finding the area of, I'm hoping I can give this to you in a way that makes this a little easier to remember, okay? Because I know there's a bunch in these 2 sections. So we're going to start off with a parallelogram, because as we saw at the end of section 8.2, there's a bunch of figures that are related to a parallelogram. So the area of a parallelogram is given like this. The area, which I'm just going to use a capital A, is just the base of the parallelogram times its height. Now the height isn't always another side. Okay, so I just want to define for you, I'm going to put a little asterisk here. The height is the distance between your bases, okay, your 2 parallel lines. So the height is equal to the distance between the bases. So right below that, you see the first example, our first parallelogram. And so I just want to clue you in on what I mean. We're going to find the area of this. Okay, so what measurements would you propose to me form the base and the height of this parallelogram? Okay, so we are given this dotted line distance right here. That's the height between these 2 parallel lines. So that means that it's that measure of one of those parallel lines that forms the base. Okay, so this 0.25 over here, that is arbitrary. That's just given as a distractor. That's not the height of the parallelogram. The height is the distance between the bases. So it's the 25 centimeters times the 24 centimeters. The 25 is the base, the 24 is the height. Now, a question that I get, you might be thinking this is, hey, Perkster, could I use the 0.25 as the base? And the answer is you could if you were given the height. And the height would be the distance between the left and the right in that case. So if you were given this straight line distance, which I'm just going to dot pink here. If I was given this distance between those two bases, then I could have used the 0.25 as the height. So it just depends what dimensions you're given. Okay, everybody tracking with me on that? Okay, so now that we've got that, 24 times 25 is 600. Now my units on area. Unit area is a two-dimensional unit. So I have centimeters in my base. I have centimeters in my height. What do you think centimeters times centimeters gives me? Yeah, I'm going to write that like this, centimeters with a little exponent, a little square up there. But if you don't like that, if you had too many bad algebra memories and you don't want to use exponents, then you are free to write down, if you want, square centimeters. I'm fine with that. Okay, so just make sure that you are squaring the unit somehow, okay, because that's important. It's a two-dimensional unit. Are we good so far? All right, then flip the page, and I've got a parallelogram right there for you. Go ahead and do exercise 3. All right, so exercise 3, the instructions say find the area of this parallelogram. So we've come to see that the area of the parallelogram is base times height. So which dimensions here are the base and the height? The 6 and what? Perfect. So the 13 inches is the base. The 6 inches is the height. The 8 inches I could use if I was finding the perimeter. I would need that. But as far as the area, that's just a distractor. So 13 times 6, I believe, is 78. And what is the units on this area? Inches squared. Great. Great job. Okay, that's parallelograms. I'm going to move on to the next figure unless somebody has a question, something they need to know a little bit more about. Well, when we went to the end of section 8.2, if you remember that chart, it's on the very back page of that packet. I told you that, okay, parallelogram is a very general figure and there's specific types of parallelograms. And one of the arrows I drew on that chart was toward a rectangle. A rectangle, remember, is just a parallelogram with 90-degree angles. Okay, there's no new information there. We already talked about that. I'm just refreshing your memory. So a rectangle is a parallelogram with 90-degree angles. So we're just going to use the same area formula. Okay, so again, I'm not even going to change the letters. So for my rectangle, the area is going to be base times height. Now, I know many of you, you've seen this before, and some teacher in the past said, hey, we're going to call the base and the height, since it's a rectangle, we're going to give them different fun names. We're going to call them the length and the width. That's fine. If you're a length and the width fan, there's nothing wrong with that. Again, I'm just trying to give you less to remember. Okay, so base times height is what I've got. So exercise 4, if you would take the 12 seconds, it's probably going to take you to do that. All right, so the area of this is base times height. And the reason that I can now use this other side as the height is because I've got that right angle. So that 4 feet is the distance from top to bottom of the rectangle. So the area is now 8 feet times the 4 feet. 8 times 4, I think we could all agree, is 32. And then one more time, I'm going to ask this question. What are the units on area here? Perfect, perfect. Great job. The reason I've given you another fairly relaxed one, remember a square is just a specific type of rectangle. So again, I don't really need any new information. The reason I gave you exercise 5 is I wanted to make the point that your units have to be the same on both dimensions. Okay, so on this problem, we've got 6 feet as the bottom. We've got 2 yards as the right side. So you would have to go one way or the other. You either have to put all your units in yards or all your units as feet. And it really doesn't matter either way, but just for us, let's all do feet. Okay, so go ahead and find the area of that using feet for both sides. And if you don't remember the conversion, remember 3 feet make 1 yard if you need to set up your unit ratio. Now, I know probably most of you don't need to set up the unit conversion, especially these numbers are fairly small. Feet are a pretty common unit, but just in case, because there's nothing wrong with you, if you do need to set up the conversion, we've got 2 yards, and this was from the last test. We know that 1 yard is equal to 3 feet. Okay, so if you need to do this to convert your units, this still applies. So what this is 6 feet. Again, you might not have needed to do that. You might have said, oh, that's just a square. So 2 yards has to be 6 feet. That is great. So this is 6 feet right here. So my area of this square is going to be 6 feet is the base, 6 feet is the height. So that's 36 feet squared. All right, I'm going to move on to the next figure. That is parallelograms in pretty good detail, unless anybody needs more from me about parallelograms. We doing okay? Okay, well then the next figure is a triangle. Okay, and so the reason I've presented a triangle next is because a triangle is just half of a parallelogram. And you might say, well, how do you know that, Perkster? How do you know a triangle is half a parallelogram? Well, I'm going to go down to exercise 6, and in a minute, we're going to find the area of this purple triangle. But what I'm going to do is I'm going to pretend that I have copy and paste ability here, and I'm going to push a button. I'm copying this triangle right here, and now I'm going to flip it over, and I'm going to paste it back down. So I'm pasting. I'm just going to do this dotted because I'm not finding the area of this. So I'm pasting this triangle, and when I do that, now this outside figure does that look like a parallelogram on the outside? Yeah. So the reason I tell you this, again, I'm trying to help you remember these things. The reason I tell you that a triangle is a half of a parallelogram is because we already know the area of a parallelogram. The area of a parallelogram is what? Base times height, right? And since a triangle is half that, what we're going to do is we're just going to put a 1/2 out in front. And there you go. There's the area of a triangle. A triangle is half of what you already know how to find the area of. So please, for me, I'm going to give you a moment or two. Don't worry about this dotted line. If you drew it on your paper, don't let that distract you. All I want you to do is find the area of this purple triangle that I gave you. Yes. Doesn't matter. Doesn't matter. I'm going to use a decimal. So the area of this triangle, the area of that purple triangle is 1/2 times the base of the triangle, which is 3 inches, times the height of the triangle, which is 1 inch. And then just as was asked, I am not partial to either fractions or decimals when we're doing these problems. In fact, when we get to the end of this section, we're going to be using decimals, and I'm going to give you some rounding instructions. So I'm fine with it either way. So 1 times 3 is 3. 3 times a half, or 3 divided by 2, is 1.5, and my units are inches squared. Don't forget to square your units. Okay. All area, whatever you're finding the area of, whether it's a parallelogram or a triangle, or like the next problem that we do is going to be a trapezoid, the units are always square units. Okay, so the next figure is called a trapezoid. Again, we saw that. That's not new information. That's just me putting a blank on the page so that you don't fall asleep on me. And if you remember the way we defined a trapezoid has one pair of parallel sides. The other pair of sides have no relationship. So you can see that in this yellow example right here. The top and the bottom are the parallel sides. The left and the right are not parallel. Here's how I like to remember this. Okay, again, because trapezoids go a little bit off kilter here, because I can't just have plain old base times height, because the bases are different lengths. So because the bases are different lengths, here's how I like to remember this. The area of a trapezoid is not base times height, but because they're different lengths, it's the average of the bases times the height. So it's kind of the same format. Again, I'm trying to help you remember this. Instead of remembering a formula, you can remember average of the bases. Now, if I told you you had 2 test grades in this class, how would you find the average? What would you do? You would first add them up and then divide by 2, right? That's how you find an average of 2 things. So here's the formula. If you love formulas, here it is. Okay, so here's the formula, but it's just average of the bases times the height. The formula looks like this: base 1 plus base 2, whatever those 2 parallel sides are, divided by 2 times the height. Average of the bases times the height. So whatever's best for you. Okay, I'm just trying to give you a way to remember a lot of information. So average of the bases times the height. It's the same format as we've been using. So I'm going to do this problem with you in just a moment, just giving everybody a chance to write this down and stay caught up. So the area of this yellow trapezoid, I also see that I have units that are different here. So before I do anything, I see that I've got 2 feet here in the middle and everything else is inches. So I'm going to change feet into inches. So I'm going to come off to the side, 2 feet. And again, you might not need to do this. Okay, again, inches and feet are a pretty common measure. So you could probably do this in your head. But in 1 foot, I have 12 inches. So 2 times 12 is 24 inches. So when I go to do this height right here, it's not 2 feet. We're going to use 24 inches. So here goes. The area is the average of the bases. What are the lengths of my bases for this trapezoid? Okay, 5 plus 19 divided by 2. And then the height is 24. So we'll put a 24 right there. 5 plus 19, that's 24. So 24 divided by 2, that means the average of my bases is 12 inches. And then my height is 24 inches. And when I throw that down into my calculator, what's 12 times 24? Anybody got that for me? 288. Thank you for the quick fingers. And so 288 and my units are inches squared. Is everybody tracking with me on my average of the bases and what that means? Okay, well then let's keep going. I think I got a trapezoid at the top of the next page for you. So I'm going to give you a few moments. The area of that is going to be average of the bases times the height. All right, so the area of this figure, again, it's a trapezoid. It's got one pair of parallel sides. So because those bases, those parallel sides are a different length, that's what clicks in my mind, that I can't just do plain old base times height. It has to be the average because they're different. So the average of the bases is going to be 16 inches plus 6 inches. Those are the bases divided by 2. And then the height, meaning the distance between the two bases, is 12 inches. So inside the parentheses, when you pop this into your calculator, 16 plus 6 is 22. Divided by 2 is 11 inches. And then the height is 12 inches. And 11 times 12 is, thank you very much, 132 inches squared. I've got one more area problem. As far as what we're doing now, this is a mild application problem, just trying to apply this a little bit. So exercise 8 says this: you want to put some new carpet in your living room. So the price to install new carpet is $8.19 a square foot. If you want to install carpet in a room that is 25 feet by 13 feet, we're just assuming it's a rectangle. Okay, what would the total cost be? So you have two things to do. Okay, I'm gonna leave the second step a mystery and see if you can figure it out. And if you can't, that's okay. We'll talk about it together. But step one is I need to know how big the room is. So you can do that part at least. Then see if you can figure out how to determine the cost from there. Okay, the first part of this that I'm hoping didn't give us any trouble, and if it did, let's please talk, okay, is to find the area of this room. So I've taken my tape measure out, I have measured the length and the width of the room I want to put carpet in, and I noticed that it's 25 feet by 13 feet. Okay, so base times height, it's just a rectangle, which is just a parallelogram, so base times height, and that turns out, what is that when I multiply those things together? 325 feet squared. Are we good so far? Anybody struggling? You were answering the am I good? I asked 2 questions in a row with different answers. That's on me. I'm sorry. Okay, so we're good. Now, what do I do to figure out the cost to put carpet on that? Yeah, so what we're told is that for each square foot, for each 1 square foot, it costs $8.19. So for 325 of them, I've just got to take the 325 times the $8.19, and that's going to come out to be a big number. What's that? $26.6175. Do I have confirmation of that? Is that good? Excellent. So yeah, that's just figuring out the cost. It's a mild application problem just to keep these at least a little bit interesting as you're going through your homework. Okay, we're going to change topics for a brief period of time. Then we're going to come back to area to finish out this section. Okay, so the next thing briefly is, since we got on the topic of triangles a few minutes ago, the topic that's related to that's called the Pythagorean Theorem. Our favorite Greek mathematician Pythagoras, a few thousand years ago, he came up with this. Well, he didn't invent the Pythagorean Theorem. Okay, the Egyptians used the Pythagorean Theorem. We have proof of that. The Babylonians, some older cultures that I'm forgetting, they used it mathematically in their arithmetic. Pythagoras's claim to fame is he codified it. he proved that it has to be true using symbolism. So that's why it bears his name. And so what Pythagoras realized is this: if you have any right triangle, so that's the key. If you have any right triangle, well, let me over on the side do my best Wednesday morning attempt at drawing a right triangle. So wee, like that and like that. I probably should have just cut and pasted one on there, but I want to impress you with my sketching skills. So there we go. There's my sort of right triangle. That's why I put a little box in there so that we can prove it's a right triangle. Traditionally, you could use any letters you wanted, but traditionally the letters, for whatever reason, math people use for a right triangle are A and B for these two sides. Now, these two sides that surround the right angle, these are called legs. Okay, so this is a leg right here, and this is a leg, the two sides that emanate from the right angle. And then the letter C is traditionally used for this longer side, and this longer side is called the hypotenuse. And so the interesting thing, before I tell you what the Pythagorean theorem is, so we take for granted like our ability to write down numbers and write down multiplication like we did up here, and to use exponents to square a thing. Like we've inherited all this from thousands of years of the development of math. When Pythagoras did this, you don't have to write this down. This is just me now being a math geek, so sorry about that. When Pythagoras did this, the way that they would have notated multiplication was pictorially. So if they had said, I want to square something, what they would have done is for this side is they would have drawn a square right here. And so then this side B, they would have drawn a square right here. And then for the hypotenuse for C, you can go back in the history books and you can look at his drawings and how he proved it. And what he would have said is, instead of how we would say it in just a minute, he would have said the square, the area of the squares made by these two legs is equal to the area of the hypotenuse. And he has a really cool proof, drawing some angles and things like that we're not going to go through because I don't want to make you dizzy, but it's pretty cool. And there's other ways to prove the Pythagorean theorem, but it's just always interesting to me that, at different points in the history of people, they've thought differently about numbers and operations and being able to use them. By the way, I'm just going to give you a shameless plug. If you need another math credit and you're enjoying this class, I do in the fall, I've got an MGF 1107. It's explorations in math. And we do in the first unit, talk a little bit about the development of numbers, and Roberto's in that class. And he can either tell you that it's worth taking or not worth taking. And you don't have to do that in front of me, Roberto, but I'm sure he would say that it's an amazing experience, well worth every penny he's paying for it. Okay, so if you have any right triangle, this is the Pythagorean relationship between them. It says that a squared plus b squared. Okay, when you square the length of one leg and then you add it to the square of the length of the other leg, that is going to be equal to c squared. And that simple relationship applies to any right triangle. So there's other things I'd like to say about that, but you're probably bored with me already. So what we're going to do is we're just going to move down the page and apply this. So here's my example. I'm going to work example 4 with you. And all we're going to do here is we're going to figure out the missing side. So in example 4, the missing side here is the hypotenuse. So let's just go ahead. So tell me, what's one of the legs that I'm going to square? Okay, so 8, we're going to square that. Great. What's another one of the legs I'm going to square? Okay, 15. And then the hypotenuse in this particular case, I don't know the hypotenuse, so that is c squared. Okay, remember the hypotenuse is always the side that is directly across from the right angle. Once you've done that, the rest just becomes a calculator problem. Okay, so when I go into my calculator, 8 squared is 64. 15 squared, I think we would come up with 225 is equal to c squared. Then again, I'm going to use my calculator to add those two numbers. 225 and 64 becomes 289. And then here's my question to you, so we can finish out the problem. Here is my lovely TI-30XA, lots of letters. Here's my calculator. What button am I going to hit on the calculator in order to turn c squared into c? The square root. Just as an aside, if whatever calculator you're using, if you don't know how to take the square root with it, or if you don't know how to square, see me after class, or raise your hand during the next example. It'll take us 4 seconds to find the appropriate button on your calculator. So on mine right here, I've got, let me zero it out. I've got 289. My square root button is right there by the division button. So I'm just going to hit that. And it turns out that C has the value in this case of 17. And I'm going to put the units back on 17 yards. Okay, would be my units. Now on yours, I just want you to make note, we know the hypotenuse on your problem, we don't know a leg. So you're going to have a slightly different step, a little bit of a different algebra in there. So if you can't quite get it, it's okay. I'm going to remind you in just a moment, but do your best on exercise 9, please. All right, so first tell me, what's one of the legs that I'm going to work with here? Again, 8, so I'm going to square that. What's another one of the legs? Okay, so here's the thing. Same thing happened in my class yesterday, so I'm super happy that you brought this up. I know we know the 10, but the reason that the reason a leg's a leg is its position. The legs are the sides that are right around the right angle. The 10 side is across from the right angle. That's always going to be the hypotenuse. Okay, so just keep that in mind. If you made that mistake, that's okay. Self-forgiveness, it's okay. You're learning, a common thing to do. But the other leg is going to be the a squared. Okay, so those are my legs. On the other side, 10 is the hypotenuse. So I'm going to put 10 over there. We always put the legs on one side of the equation. We always put the hypotenuse on the other side. That's 100% without a doubt, no matter what. Okay, now I'm going to use my calculator like we did before. 8 squared is 64, and a squared, and 10 squared is 100. Now this is the point where if you put the things in the right way, we come up with something a little different than previously. Previous problem, both my numbers were on the same side, so I was just able to add them up. But this time, my numbers are on a different side. So what do I have to do to get the a squared alone so I can take the square root? Yeah, I'm going to have to subtract the 64. By the way, the reason I gave 2 different problems is because those are the only 2 things that can happen. Okay, so you're going to see one of those 2 things on your homework or on the test or on the quiz. So there's no third option as far as what could be the missing side. So I got a squared is equal to 36. And when you hit the square root button, or you probably didn't need to use your calculator for that, a is going to be 6 and the units are inches. Before I move on, that's all I have to say about the Pythagorean theorem, because now, by the way, we could find the perimeter and the area of those. That might be a problem that I ask on the test, might be something like fill in the missing side and then find the area and the perimeter, okay, just to get 3 problems with one figure, okay, but now it's just a triangle. You know everything you need to know. Any questions before we move on? All right, last page, I believe. Yep, we're on the last page, so you're doing good. You're all still awake. I'm proud of you. All right, the last page here, a circle. So This is the first time in this unit or in this chapter, if we include the sections from chapter 8 we did before the test. This is the first time we've encountered circles. Okay, a circle is just a figure in the plane. So the definition of a circle is all the points in a plane the same distance from a reference point called the center. So a circle is all the points in a plane that are the same distance from a reference point called the center. So I'm going to do my best to draw a circle. I drew a really good one yesterday, so hopefully you get just as good Perkster today. Hang on, I can't talk and draw. Shh. Oh, it's already no good. Sorry, everybody. You can get your money back. Okay, but that's the best attempt at a circle that I can make today. I'm sorry. The reason I'm drawing a circle is I just want to talk about a couple things about the circle. So here's my center point. The center is not part of the circle. It's just the reference. But now this distance that I go all the way around, the distance from the center to the outside, that should be the same all the way around. Does anyone remember from seeing this before what that's called? Yeah, that's called the radius. That value never changes. If I wanted to draw a line from one side of the circle to the other that goes through the center, I'm just going to make it dotted so that I don't mess up the drawing too much. Does anyone know what that line is called from one side to the other through the center? The diameter. Great. What's the relationship between the radius and the diameter? Perfect. I'm just going to write that to the side because that'll come up in some of your problems. The radius is 1/2 the diameter. Great. This is just bonus trivia for you, so you can share it with friends at parties this weekend or family members when you're having dinner. The diameter is actually a specific something called a chord. A chord is something that goes from one point on the circle to another. Okay, that's called a chord. And the diameter is a specific chord that goes through the center of the circle. You can see there's a relationship. If we had time, there's a relationship between music and math. It's not accidental that this is called a chord. There's a reason for that, but we don't have time here. Different day, different class. Okay, so the two things for a circle. So the perimeter of a circle gets a fancy word, not a family word, but a fancy word. The perimeter of a circle is called the circumference. I am sure at some point in the history of language, there's a reason for that, but language is not always my gifting. Okay, so the circumference of a circle, the distance around the outside of the circle is given by this. It's given by 2 times this number that I'm going to talk to you about in just a second. It's a Greek letter pi times the radius. The circumference of a circle is 2 times pi times the radius. And so you might be saying, well, what is pi? Pi actually is defined to be the ratio of the circumference to the diameter of a circle, what that's going to be. And that the interesting thing is it's the same for every circle, no matter how big or how small it is. But the issue with pi is it's what's called an irrational number. Irrational numbers never end and they never repeat. Okay, so they are always different. If you're interested in what the digits of pi looks like, Google digits of pi. You can find a lot of very bored people that have mapped out the digits of pi to millions and millions of digits. And there's one person that has arranged it into wallpaper. So you can make pi wallpaper if you're looking for new decor idea for your room. Most of the scientific calculators have a pi key. So it gives you good decimal places of pi so you don't end up with round off error. If you're just using a basic 4-function calculator, then the approximation that I recommend for pi is that you should use 3.1415. That would be the approximation that I would recommend using. Go a couple digits out so that you don't end up with round off error. Now on the test, I will tell you to either use your pi key or 3.1415. I will grade for both. Be careful in my math lab. Okay, follow their instructions. Okay, because you don't want to have done the problem right and then end up with round off error and think that you're wrong. Okay, my math lab is sometimes fussy like that. The area of a circle, so the measure of the region inside, the area of a circle is again this number called pi times the radius squared. So the first example is going to be my example. I am going to do the, we're going to go one at a time. I'm going to do the circumference of example 5. So the circumference is just 2 times pi times the radius. So here we go. 2 times pi times, what's the radius of this problem right here? Yeah, it's right there in front of our face, but I just want to make sure everybody's still awake. So 2 times pi times the radius. So here's my calculator. Let me see if I can get rid of the glare. Oh, no more glare. We'll put the calculator over here. So I'm going to go ahead. So 2 times, notice my calculator does have a pi key right here. So again, if you want to know, maybe you can't see if your calculator has a pi key or not, just see me after class. I'm going to hit that. And so notice the pi key takes pi out to a bunch more decimal places. So you're not going to encounter any round off error. And then times 6, we're going to round to the hundredths place. We're going to round to the second decimal place. So this is 37.699. So my hundredths place is the first 9. Remind me the rules for rounding, just in case it's been a while for you. What do I look for in the next place? If it's 5 or more, what do I do? Round up. If it's 4 or less, what do I do? Leave it alone. You truncate, or just you just drop the rest of the digits. So this is 5 or more. So the 0.69 rounds up to 0.70. Yes. So it's going to be 37.70 centimeters. Again, circumference is a linear measure. It's the distance around the outside. So that's why it's 0.70. All right, if you would please exercise 10 right below it, if you could go ahead and find the circumference of that. All right, so the circumference of this circle is 2 times the number pi times the radius, but this time, hopefully you weren't fooled. I gave you the diameter. So what number did you plug in for the radius of this problem? Okay, so 4 yards, great. So then I get my friend the calculator out. I've got 2 times pi times 4 yards. So 2 times the pi key times 4. I'm going to round it to the hundredths place again. So I have 25.132. And so I've got my 3. There's a 2 behind it. So this becomes 25 point what? 13. Yes, we just truncate and we have 25.13. We okay with that? Okay, then going back to the previous problem, I'm going to go ahead and find the area. Hopefully, once you remember the formulas for these two, I'm hoping that this is not too big of a deal. It's just kind of plugging and chugging along. So my area, I'm just going to do it over here on the other side where I've got some space. The area is pi times the radius squared, so 6 centimeters. I'm going to square that. So when I square 6, 6 times 6 is going to give me 36. So I'm going to take 36 times the pi key, and that's going to be 113.097 and some change. So I'm going to again round to the hundredths place. So that 7 tells me to do what with the 9? Round up. And so it becomes, instead of 09, it becomes 10. It becomes 10. So 113.10. This is area. So what is the units going to be on my area? Perfect. Thank you. Well said. Centimeters squared. Awesome. Anybody got anything you need to bring up? Any questions, comments, concerns? All right, well then find the area of exercise 10, please. So the area of this problem is going to be equal to pi times the radius squared. And you already told me the radius previously. It was 4 yards. So I grab my calculator, 4 squared, 4 times 4 is going to give me 16. And then I'm going to hit the pi key times the pi key, and I get 50.265. And then the rest of it is beyond what I'm concerned about. So when I round this to the hundredths, the 0.26 becomes 0.27. So I've got 50.27 yards squared. We just got a couple wrap up problems. So before we get there, are there any questions? Anything that I've done a poor job and need to clear up for you? Because it's going to be like 5 days before you see me again. And I know you're going to miss me, but I want to make sure you do your math well. Okay, so the last couple problems are just combo problems. So exercise 11, notice what we have here. We've got, what's the figure that is the bigger figure? What's this figure that I'm tracing right now? It's a parallelogram. I've got a parallelogram, and now somebody has come along and cut out a circle in the middle. And so my question to you is, how are we going to find, what operation will we use to find the shaded area, what the blue area? I can find the area of the circle, sure. And then what else do I have to find the area of? Parallelogram. So I've got both areas. That's exactly what you're going to do. So if you can't do anything else on the problem, you can do that. But then what am I going to do with those two values? You're going to subtract because somebody's cut a hole. When I cut it away, it's now gone. And I want to see what's left over. So one little thing. This first one, I'm gonna leave it to you to try to figure out. And remember, self-forgiveness if you don't see it. That's why I've got a second problem. It's going to be the same sort of thing. You can find the height of the parallelogram with the information given. Okay, so go ahead. I'm going to give you a couple minutes. Find those areas, do that subtraction, and see what the shaded area is. All right, so the area of the parallelogram. The area of the parallelogram is base times height. Well, I think we can all agree that the base is 10 feet of this, but here's the part that this is the reason I gave this problem. So again, don't beat yourself up if you didn't see this. Hopefully it'll become clear in a moment. What's the height of the parallelogram? 4. And we could get that because why? Perfect. The circle goes from top to bottom of this parallelogram. And so if the radius is 2, 2 plus 2 gives me 4 feet as the height of the parallelogram. So again, if you didn't see that, that's okay. There's nothing wrong with you. Okay, it's a tough thing sometimes to notice. So the area of the parallelogram, 10 times 4 is 40 feet squared. The circle is a little more direct. The area of the circle is just pi times r squared. So pi times the 2 foot radius squared. So that is 4 times pi. So 4 times the pi key gives me 12.566. So that's going to be 12.57 feet squared. Before we finish this problem up, anybody got a question, a comment, or a concern? Okay, so then the ultimate question was, what's the shaded area? That blue area, what's left over? Well, you're going to take the 40 feet squared, you're going to subtract the 12.57 feet squared, and what do you get when you do that? And then don't forget your units, feet squared, perfection. Great job, everybody. All right, one more, I'm just going to give you a minute or two. It's the same sort of thing. I just wanted to make sure that we had a follow-up problem in case anybody did not do well getting the height of the parallelogram in the previous one. Bless you. Right, so for this one, the bigger figure is a square, but it's just a parallelogram. And then again, the reason I gave this is just to make sure that we're comfortable figuring out the dimensions. What are the length and the width of, or the base and the height of this square? 6. Again, it's a diameter problem, so it's all, I can go all the way across is 6. So this square is 6 feet by 6 feet. Is anyone not seeing that? Okay, 6 feet by 6 feet. So that means the area of the square is 36 feet squared. The area of the circle, which is inside, is pi times the radius squared, which is 3 feet that I'm going to square. So that is pi times 9. So 9 times the pi key gives me 28.274. So that's just going to stay 28.27. And then the area that is shaded, that orange or yellow or gold, whatever it is just the difference between those two things. And what do you get when you take the difference between 36 and 28.27? Perfection. Great job.